has a big overlap from what we've done in the past. We're essentially going to be focusing on finding confidence intervals to estimate a single proportion. And there are two types. This one down here, we're not going to do very many questions on them at all, but I'm putting them in there because they do have some, where we're going to calculate what's called the conservative margin of error. So you've met that guy before. Remember, the conservative margin of error is just simply 1 over the square root of the sample size, right? And if you want to calculate a conservative 95% confidence interval, so the word you're looking for here is conservative margin, confidence interval, conservative margin of error. You see that word at the beginning, then you are going to use this formula here, which is the sample proportion plus or minus 2 standard errors, or the sample proportion plus or minus 2 times that guy. The answers are virtually identical, so it doesn't really matter much, but probably use this one. And that's great. We're going to do one of those. Let's do one of them right away then. That sounds like just to get them over with. There's very few of those, but let's imagine we did one. So someone collected a sample of 200 people, and they went and asked them a question, and the question they asked them is, would you like to be younger? Now, the funny thing about asking people, would they like to be younger? It really strongly depends on their age. 12-year-olds want to be older. 40-year-olds want to be younger in general, right? So you get up 200, any age at all, and you found out that 59% of them said that they wanted to be younger. Right? And we are going to create a conservative margin of error, a 95% conservative margin of error. So let's first get this guy, because question A might well be, find the conservative, let's call it margin of error, because I don't want to keep writing all those words. It's simply 1 over the square root of 200. You see, it doesn't even use that number. And so, where are we? 1 divided by the square root of 200 ends up being 0.07 to 2 decimal places. And part B is find a conservative (95% confidence interval. And the formula for that is the sample, give or take 2 margins of errors. Well, we know that this guy is 0.59, and 2 times this guy is 0.07. So it's going to be 0.59 plus or minus 0.14. And on the small side, that gets me excuse me. Itchy nose here. So we're going to get 0.45, and it's going to be up to 0.73. And so I like percentages. So we would estimate somewhere from 45 up to 73% of the population would like to be younger. And then you could do some newspaper article where you talk about how people want to be younger. And then after that article, if it's an online one, won't there be lots of adverts which will be, use this cream, it'll make you look 10 years younger, and go on this diet and you'll look 5 years younger, all the kind of things that they associate. So have you ever noticed that when you read an article about something, there's very often these annoying adverts in some way or other connected to whatever it is you're reading, right? So I think they call that focused advertising, right? I've been told this, I'm not really 100% sure it's true, but in our house, we've got one of those things that you can talk to and it tells you stuff, right? So we say, hey, Alexa, what's the weather going to be like? And people have told me that they've had conversations. Let's say it's a conversation about buying a new car. And then they go online and there's all these buy a new car adverts that suddenly appear. And their suspicion is that Alexa listens to your conversations and then sends that information to your web browsers, and your web browsers then do focused advertisement. Is that me? I don't know if that's true, but do you think that's possible?
Yeah, that's definitely true.
You've got evidence, or you just know that from your own experience?
Yeah, no. There have been people who have worked for like Amazon and Google who have actually been fired for saying that's actually how they can manipulate their software to suit you better, when in reality it's just like trying to
listen to your conversation.
To you.
Okay. So back to this question: are we comfortable with the conservative margin of error? Right? It's not a. It does a job, but it's not very accurate. Let's just put it that way, right? So what would the more accurate version look like? Well, they look like this guy here. So these are normal or approximate. It's a bit strange me saying that this is more accurate, but it is. And the formula that you're going to use to calculate a 90 or a 95 or a 99% confidence interval, because these three are the industry standard, right? So if you look at, you know, medical papers, clinical trials, you know, whatever it might be, government estimates, one of these three, if they use confidence intervals at least, is going to be used, right? People don't do a 93% confidence interval because they feel like it, right? Or at least they shouldn't, right? They're standard. 90, sample proportion, plus or minus a really weird decimal, but it works, 1.645 times your standard error guy. Now, your standard error is the guy we met yesterday. You remember that square root of p, 1 minus p over n guy? That's him. And this is the same guy here and here. So if you want a 90%, it's 1.645 times that. Do you see how that's not quite 2? Can you see that's not quite 2, but almost 2? Right. And if you wanted a 99% confidence interval, then you would use this number. And this number actually depends on which textbook you use. I'm just rounding it off to 2, which is pretty common. I believe it's 2.576. It's also 2.575 in other textbooks. This one up here is sometimes called 1.64. I'm using the 1.645. When you think about it, isn't it very minor differences? So the chances are that when you round the answer off, it'll be the same number. But be aware of that when you're doing WebAssign, that if WebAssign thinks it's 0.123 and you think it's 0.124, couldn't that just be a rounding off issue caused by which version of this number, you know, was being used? So as long as you think the calculation's right, you may want to tweak the last digit just to see if you can get WebAssign to say, that's the same guy as me now. So let's break this down into little jobs, and then we'll kind of move from there, right? And build the whole thing. So if I have a sample of 200 and my p hat is 0.55, then let's focus on getting that guy. He's the square root of p hat 1 takeaway p hat all over n, and let's do it to 3 decimal places. So pretty much, once you know the right formula to use, you do it all in one go. Square root 0.55. Okay, what decimal is 1 point? I almost said the answer. What is the decimal for 1 takeaway 0.55? 0.55. Who's the other guy?
4, 5.
Yeah, 4, 5. And then divide everything in this case by 200. And the answer should be 0.035. You comfortable with that?
Wasn't,
Yes.
shouldn't it be 0.45
Isn't that
in
what
your
I typed in?
calculation?
I think I did 0.45.
Okay,
did.
I'm seeing things weird. Sorry.
Okay. You got to stop drinking whiskey when you take my class. Just telling you that right now. Okay.
I'm gonna have to drop out then.
Uh-oh. Oh, God, I'm in a bad effect to my students. Okay. So I'm just focusing on that job right now, right? So that would be the end of my question. Let's do a huge sample. 2,000, actually. If you look into the details, do you know almost every survey that people do, every poll, the going rate is about 1,005, 1,010. 1,000 is a nice big number that gives you good accurate data. If you make it any bigger, you get more accurate answers, but it becomes even more expensive. So there are companies like the Gallup poll, for instance, and Ipsen and all sorts of universities of their own, and they charge money, right? You go to them and say, I want to know something. How much is it going to cost me? And I'm pretty sure they say, well, we have the 1,000 sample one, that'll cost you X amount of money. We have a 10,000 sample one. That's the Ferrari, that's the expensive one. And we have the Bill Gates ones, right, where we ask 1 million people, right? And each one of them is more accurate than the previous, but the kind of, what's the thing? Do you know the law of diminishing returns?
Yeah.
Doubling the sample doesn't double your accuracy, right? It kind of drifts away to, it doesn't matter. So in this case, they got this fella. Oh, and I forgot to tell you what the story was. We're going to do the same number as before. And so it's still going to be p hat 1 takeaway p hat all over n. And the numbers are going to be the same two numbers on the top, 55 and 45. I'm going to have a different sample size. Before I do this on the calculator, do you think this answer is going to be a smaller standard error than the one we got when we only had 200? Do you think this is going to be a smaller answer? Agreed? Is it kind of obvious? Divide by a big number, small answer. What it's not going to be is 10 times smaller. In other words, 0.0035. The law of diminishing returns. So let's see how much smaller it is. 0.55 times 0.45, all divided by 2,000. And it ends up being 0.011. It's roughly, very roughly, about a third, right? If you divide that by 3. So do you see, you might spend, twice as much money, but you don't get twice as much accuracy, right? And that's a truism in samples. Are we cool then if I just tell you those two guys? Are you comfortable about finding this fella? Right. So if I tell you sample size and p hat, are you comfortable about finding the standard error? So let's now get a guy called the margin of error. And in particular, let's do a 95% margin of error. The margin of error that I'm talking about is the name we give to these two things when you multiply them. That's called the margin of error, right? This guy times this. Now, since I want a 95% one, it's going to be this one times that, right? 1.96 times it. So I want a 95% margin of error. The p-hat is 0.2. The sample size is 500. Okay. So the margin of error is going to be 1.96 times the standard error. P-hat, 1 minus p-hat, all over n. The 1.96 is a fixed number, right? If you're doing a 95%, that's fixed, right? If you're doing a 99%, you see how that number is fixed as well, right? And this thing over here kind of depends on these two guys, so that will change each question, but it's a 0.2, a 0.8, all over 500. And so what I'm now going to do is see if we can do that on the calculator. So it's going to be 1.96 times a square root of this guy, 0.2 times 0.8 divided by 500, and the answer ends up being 0.035 to 3 decimal places, or as I prefer, 3.5%. So if you were listening to a television program about the primaries and they went and said, the latest is in, and blah, blah, got X amount of percent, and the margin of error was plus or minus 3.5%. If you ever wondered where the plus or minus 3.5% came from, now you know. You see where it comes from? It comes from 1.96 times the square root of the people who said they were voting for the guy, times the people who said, I'm definitely not voting for the guy, divided by the number of people you talked to, right? And that calculation gives you margin of error. So that if you know what p-hat is, can't you then, you know, that's what the next stage is going to be, put all the pieces together. I'll be able to give you a 95% confidence interval, and I can tell you, 95% sure that this is where the real answer is going to be when the election is over, right? When the primaries are finished counting everybody. Are we good with that one? Right, let's try a 99% margin of error. And in this one, p-hat was 52, and the sample was 1,024. And the margin of error, well, in a 95% world, it's 2.58 times this guy. You see, it's the same formula, just with a different fixed value. In this particular question, then it's going to be 2.58 times 0.52, 0.48, all over 1,024. So here goes. 2.58 times square root of 0.52 times 0.48 divided by 1,024, and the answer I got here is 0.040, or essentially 4%. You comfortable with that? Now, I said that depending on the textbook, this number wiggles a little bit, right? One of the answers that you could use is 2.576. So let me just show you what that answer would look like. And instead of 5.8, I use 2.76. You notice that's the only thing that changes, right? Now I'm about to hit answer. enter here and see the answer. That's the answer we got, you see it? Now, would you agree that 2.58 and 2.576 are pretty much almost the same? But it will make a difference. Let's see if it's important. 0.0402. Didn't make any real difference at all, did it? I mean, if you look at the answer above, isn't it 028 and then it's 021? I mean, you had to get to the 4th decimal place before there was any significant difference. Can you see why in the big scheme of things, it's not too important, right? If it's 2.58 U's or is it 2.576, or if it's, in my case, 1.645, and in some books it'll be 1.65, right? So if you look at another video and they use a different number and you're a little bit worried, can you kind of see in this example, it really isn't much. It might, in one of your questions, need a 4-0 to be called a 4-1, right? Just in the off chance. And I've said, look, if you're 99% sure you've done everything right, just tweak the number, right? Call it 041039 and that'll probably get you, right? Save you a whole lot of grief. I think this is going pretty good. Cody, do you like these questions? Looking good? Lots of calculator stuff, but yeah, that's fine. So are we good with margin of error? Do you want me to do a 90%? Because it's the only one I've not covered. Are you comfortable about how we calculate the margin of error pieces? Yeah, okay. Then let's put the whole package together. Let's get, let's do a 90% confidence interval then, right? From scratch to, start to finish, the whole thing. So let's do some audience participation. I'm going to use you lot to get an answer. So to remember how this is going to work, if you are a yes person, you're going to do that, okay? So I'm going to cheat a little bit here. Okay, I don't know how to make my little thumbs up go away. Is that it? Yes, okay. No, that doesn't make it go away. Do you just wait and it goes away? Okay. What do you mean, no, you wait?
Yeah, it just appears after a minute.
Okay, so that's fine. Now, what's my little bit of chain? If I only counted you, right, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right, if I only counted you as real people, my sample would be 19, which is far too small to get any kind of accurate interval. So you don't know it, but every single one of you is actually 100 people, right? So you have to be really good at your voting here. Okay, so here is the question. If you like war movies, right, with explosions and heads getting blown off, vote now. Do you like war movies? Okay, we have an answer. Let's move on then. Oh, somebody told me that they like Rambo movies. They count. So war movies, we got 6 out of 19. But in reality, that's the real answer. But in the pretend world, wasn't the sample that guy, right? I said 100, didn't I? There we go. Now I'm going to turn that into a decimal, because decimals just work better with calculators. 600 divided by 1900. And the answer I get is 0.316. So the 3 decimal places, 31.6% of you. And we are going to find a 90% confidence interval based on this data. So the formula is p hat plus or minus 1.645 times the standard error formula. P hat is 0.316, give or take 1.645 times and the standard error formula, which looks like this guy. So this becomes 0.316 plus or minus 1.645 times P hat, which is 0.316. Take that away from 1 and you get 0.684. And you're going to divide it by allegedly 1,900 people. And what I'm going to do now is that guy, which is the margin of error piece. So let's see what we have. And 1.645 times the square root of 0.316 times 0.684 divided by 1,900, and we get 0.017. Well, let's be a little bit more accurate, 5. So if I take that away from that, let's see, we got 0.316, take away 0.0175. That gets me 0.299 to 3 decimal places. And if we add it, 0.316, and we add 0.0175, we get 0.334. And since I like percentages, I am making the estimate based on a 90% confidence interval that the percentage of American students who go to community colleges, because I think that's probably the population that you best represent, would you agree? Community college students rather than anything else. That somewhere between what, 30 and 33% like war movies. And I'm only 90% confidence, agreed? Isn't there a 1 in 10, right, a 10% chance that couldn't the real answer be a lot more than 33 or a lot less than 30? But isn't it quite a nice interval? I mean, it's, 30 to 33 is not a big, right? Not a lot of wiggle room. So you do get an idea of what that answer would look like in, the big scheme of things. Now, I've made some assumptions here, which one of them is obvious, which is how many people I asked. But can we pretend I really did ask 1,900, right? That I went to, various colleges and, done that. If that had been true, then we have got good data to represent what the entire population of community college students feel about war movies, or abortion, or political party they're going to vote for, or do they think even community college is worth the money that they're spending, or whatever it might be. By the way, I hope that last answer is yes, because you're the reason I still have a job. So let's hope that you think it's worth the money. That's basically the process, right? And so we're going to do some more practice at creating that. And then I'm going to add another level after we've created this interval. And that is, what kind of evidence is this giving us, right? So let's suppose that we are interested in, let's do the politics one. It's always a good choice. We're interested in who's going to win the Bremerton election, right? Mayor's election. And so we collected a sample of 350 and we asked them, are you going to vote for the Democrat candidate, right? And the number out of the 350 that says, yes, I intend to vote for that Democrat Party. Now I'm going to create a little number system here. And 182 of them said yes. And I wanted a nice number, so that's what I was doing, right? So 52% of them would be, yeah, I'm going to vote for the Democrat guy. And let's see if we can find a confidence interval. Actually, we're going to find two confidence intervals. First one I'm going to find is the 99% confidence interval. Now, when I get this one, won't I be 99% sure that the numbers in my interval contain the real answer to what everybody in Bremerton is going to do, right? 99% sure. So that's the kind of percentage where I might not bet my house on it, but I'd certainly bet whatever money I've got in my back pocket, right? If I was a gambler, I'd feel good about betting on this being true, right? Is there a 1% chance I got it wrong? Yep, there's always going to be a percentage chance, no matter what you do, of being wrong. So this fella is going to be p hat plus or minus 2.58 times the standard error, which is p hat plus or minus 2.58, the square root of p hat 1 minus p hat all over n. And this is going to be then 0.52 plus or minus 2.58. And then this horrible mess here, which is going to be 0.52, 0.48, all over 350. So I'm going to get this guy first. 2.58 times the square root of 0.52 times 0.48. Oops, and I forgot to divide by 350, didn't I? And we get 0.52, give or take, and I'm rounding it off to 2 decimal places, so give or take 7%, which means it could be as 44, it could be up to 59. So what we'd be saying here is 45% up to 59%. So this is our prediction on what everybody in Bremerton who voted would do. Somewhere between 45% of them are going to vote for the Democrat guy, but it could be all the way up to 59%. So here's my question. Is there enough evidence in this interval to say that the Democrat is going to win the mayor's election? In this interval, is there enough evidence to say that the Democrat is going to win?
No.
Correct. Remember these interval values. Isn't every single one of them just as likely to be true as any other one? So if he ended up actually being 45 or 47, wouldn't he lose? Because we'll assume the other guy got the other 53. So he would lose. If it was this number up here, wouldn't he for sure win? But isn't there a very good chance that he could lose as well? So in this case, wouldn't we say too close to call? Now I'm going to do a 90% confidence interval. And the 90% is this guy, plus or minus 1.645 times the square root of p hat 1 minus p hat all over n again. So it's going to be 52, give or take 1.645, and the same calculation as before. In this case, let's find out. Should be able to, can I get the answer back? I can, good. Which means I can just go here and change only one number, 1.64, insert the 5, And I get the answer, 4%. And that means it could be as low as 0.48 and it could be as high as 0.56. So in this case, it's 48%, but it could be up to 56%. A couple of things. Have you noticed that this interval is much narrower? Right? 48 to 56 isn't a lot narrower than 45 to 59. In this particular case, would you also say that there's no guarantee that the Democrat guy is going to win, right? Because it could be 48 he got right, it could be 49, right? He'd still lose, right? It'd be a close game, but he'd still lose. So in both those, won't you use the phrase too close to call? Now, I made that come out a nice number. I wish I'd got a different kind of result. So imagine I did another election, and this is the two intervals that you end up with. In this one, you ended up with 51% to 55%. And this one, you ended up with 49% to 57%. Now, in this one here, would you agree it's too close to calling it? In this one here, wouldn't you make the prediction that the Democrat will win, right? It's a prediction, that hasn't happened yet. Because in this interval, aren't all of the numbers bigger than 50? Now, if you were in that party, the election party for the Democrat, won't you publish this one? Let's say you bought it. Won't you publish that one in the local papers? And you won't publish that one, will you? They even have a name for this because it's done. A lot of the time this is done. If you pay for a poll, right, it's your money, right? And you've paid for it to happen. If you don't like the answer, aren't you legally entitled not to tell anybody about it? It's my money. If I want to tell you what it says, I'll tell you. Not telling you. So it's not illegal to do this. But why do they do it? Well, you might think, well, it makes them feel better. And that's not the reason. If you think your candidate is going to lose, and they tell you that there's been an unbiased poll done that says you're going to lose, what do you think that does to the people who vote for that other party? Some of them don't bother to vote. It's suppression of votes. And because they don't bother to vote, guess what happens? It's like a self-fulfilling prophecy. Doesn't the other guy win? So when we get nearer to the midterms, be on the lookout for lots of polls trying to get you to not vote for your guy. We did a poll and only 20% are going to vote for your guy. It's a horrible day tomorrow. It's going to be pouring rain. Don't bother. I mean, that's kind of what they're trying to say to you, isn't it? And why are they doing that? Because they don't want you to vote. Even if your guy's only got 1%, why don't you make it 1.001%? Make them feel better, right? Always vote for your guy, regardless of what they tell you, because they are real. Some horrible things have happened, in my opinion, to suppress votes. I don't care who you want to vote for, but vote for them. Don't let these guys talk you out of it because, oh, blah, 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 it's no chance of winning. You know, it's a foregone conclusion, all that nonsense. I got that bit out of my son. I need a joke to insult politicians then. Did I tell you the joke about the guy who went to the doctors? And the doctor looked really sad and worried. And so the patient says, oh, come on, doctor, what's up? Tell me it. And the doctor says, well, I've got good news for you and I've got bad news for you. So he said, well, tell me the good news first. He says, oh, you've got 6 months to live. And he looks at him and says, that was the good news. I said, yeah. He says, well, what's the bad news? Oh, I should have told you 6 months ago. But you're in luck. There's a brand new medical. It's cutting edge. It's really just on the market. You can have a brain transplant. That'll save your life. And he goes, but they're expensive. And the guy says, look, you know, how much are you talking here? He says, well, the best way to show you is I'll take you into the room and give you a kind of, there's a range of prices. So he goes to the first table and there's big jars of brains there. And he says, look at these brains. He says, English professor brains are in there. We can give you these ones. It's going to cost you $10 an ounce because there's plenty of them. He looks, oh, okay, I could afford that. So he moves to the next table and he says, what about this one? He says, well, that's the next, you know, the next level up. He says, these are really, really good brains. He says, these are mathematician brains. These are going to cost you $100 an ounce. And the guy goes, it's steep that, but I might be able to do that. And he goes to the third one and he says, what about this one? He says, these are the most expensive brains we've got. These are politician brains. They are $1 million an ounce. And the guy shakes his head and says, no, that can't be right. He says, I might pay $1. I mean, I could even pay $100, but no way am I paying $1 million an ounce. He says, how come they're so expensive? And the doctor says, have you any idea how many politicians you need to kill to get an ounce of brain? Did you just like that joke? God, I never know where you lot. By the way, no one get killed in the making of that joke, remember, right? They are jokes, right? No one got killed. Okay, let's do one last one of these guys and call it a day for today. So let's see if I can pick a story. Question 5 has, in 2018, 8% of people, so in my sample, out of a sample of 1,000 Americans, went and said they thought the opium addiction was not too serious or not too right. So only 8% thought the opioid addiction wasn't bad, right? So if you're not into it, there's a whole load of people were becoming addicted to painkillers. That's essentially what opioids are. And then it became a black market where essentially the Chinese, I go and blame a country, but not a country, but people who are in China were producing lots of opioids and getting them through the black market, fentanyl and so on. And they're really downright dangerous thing because these fentanyls get laced with the other drugs that people take. And there is literally 100,000 young American adults essentially being murdered a year by these fentanyl overdose. Well, I'd call them poisoning that are caused by these drugs being introduced. So only 8%, which is nice and low. So that probably means 92% of Americans think it's a bad thing. Let's do a prediction on what the entire American population would think of this. So the one that we're going to do is a 95% confidence interval. So it is going to be p hat. Since it is a 95, that's 1.96. And since it's a standard error, I'm going to do p hat 1 minus p hat all over n formula. And there's my 8%. There's my 1.96. And it's going to be an 8% with a 92 over 1,000. And what do they want the answer to be? Okay, we're good. So 3 decimal places or 1 decimal place in percentage, but 3 decimal places is what we're after. So 0.08, give or take that guy. So that's 1.96 times square root, whatever it is, or 0.08 times 0.92 divided by 1000. And the answer is 0.017 to 3 decimal places. So 0.063 or 0.097 as a percentage then to 1 decimal place. We can make the prediction that we're 95% sure that if you asked every American, do you think it's not serious, you'd only get an answer somewhere in the range, what, 6 to 10% roughly. So that's our prediction on the entire population of America's opinion on opioid issues. And it's very small, as you'd expect. What would happen if I made that 100,000, if I did a Bill Gates? Right? I spent a lot of money and asked 100,000 people. What would happen to this interval? Would they get bigger or narrower?
So narrow,
Yes.
narrower, I think.
Agreed. Yeah. When you ask more people, doesn't this number here get bigger? That's the only number that will change, right? And if this number gets bigger, because you're dividing, doesn't the whole thing become smaller, right? Dividing by big numbers makes the answer smaller. And if the answer is smaller, doesn't the margin of error get smaller? And if the margin of error gets smaller, don't you only move a little either side? So it gets narrower. So it's like a seesaw, right? Big numbers, margin of error goes down, interval goes down, right? Small sample sizes, whoops, margin of error gets bigger, right? See, if you only ask 2 people, which would be stupid, right? You shouldn't. But if you only ask 2 people, couldn't the margin of error be plus or minus 90%, right? In other words, pick any number you like, it's just as likely to be true as anybody else's number. And last name, and we are out of here.